In this tutorial we will cover Chapter 2. Chapter 2 includes sets, functions, and matrices. These are the discrete structures that we will be studying in discrete mathematics. The definition of a set is an unordered collection of objects. Normally you list, it's a list of objects, there is no order to it. The definition of a set should be intuitive. It's a collection of things, objects. For example, the students in this class, the chairs in this room. A set can be can contain numbers, it can contain anything. It's just an unordered collection of objects. The objects in a set are called elements or members. A set A is said to contain its elements. We will see many examples of sets, and there is also notation that we use when we work with sets. Here is the first one. When you say this small a belongs to capital A, طبعا here that means A is an element of the set A. A is an element of the set A. If you want to say that A is not a member of A or does not belong to the set A, you use the same symbol but you just cross it. But that notation means A is not an element of the set A. There must be an underlying set or a universal set, either that is specified or it is understood. I think looking at many examples, the idea of a set should be an intuitive one. You should know what it is. We'll look at many examples, and we will most of the things we will do in this chapter is just basic set theory ideas, and the idea of sets and the way to handle sets is a useful one in mathematics. Here is an example of sets. We normally use capital letters to denote sets. For the set A contains the numbers 1, 3, 5, and 7, and we list the elements of the set in those type of brackets. Here is using the notation. 3, for example, is an element of A, while 2 is not an element of A. Here is another way to describe a set. The set C is X such that X is equal to n squared plus 1, n is an integer, and n is larger than or equal to 0 and less than or equal to 10. For the elements of the sets are the values you get by substituting different values of n in this equation. N is equal to an integer from 0 to 10. طبعا you can always list the elements of the set if you have a finite set, or as in this example you can just describe the elements of the set. Here is another example. The previous example was a set of numbers. Here is a set that contains letters of the alphabet. The set S contains the letters A, B, C, D, and again here the order is not important. This is just a listing of the elements of the set. Order is not important. For the set S, which we just listed, A, B, C, D, is the same set as B, C, A, D. It contains the same element. Each distinct object is either a member or not. If you list the element more than once, it does not change the set. Repetition is not important. The same set A, B, C, D is equivalent to the set A, B, C, B, C, D. This set contains the same elements with some elements repeated more than once. That does not change the set. If a set is infinite, we might, or even if a set is a large set, we may use the ellipses, which is 3 dots, to describe a set without listing all of the elements. Normally we do this if the set is infinite, or if it's a set, if the set is large. So we list just a few elements, and then we use the ellipses, the three dots, yani list the first few elements, then use the ellipses, and then list the last elements in the set. Here is the set S is A, B, C, D, then use the ellipses, three dots, and then the last letter is Z. This is clearly the set of all letters in the English alphabet. Here is more examples of sets. Set V here is the set of all vowels in the English language. So V contains the letters A, E, I, O, U. The set of all odd positive integers less than 10. This is O. Has the numbers 1, 3, 5, 7, and 9. These are the odd positive integers less than 10. Another example, the set of all positive integers less than 100. This is a large set. You don't want to list all the numbers from 1 to 100. So you can just write 1, 2, 3, dot, 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 and then list the last number, 99. These are all the numbers, positive integers less than 100. The set of all integers less than 0. This is the set of negative integers. Start with -1, -2, -3, and then the three dots means the set continues to minus infinity. Now there are some important sets. These are all sets that we use all the time. You need to know, we refer to them by their name, and you need to know what they are. The first set is the natural numbers. We use a bold N. The natural numbers are the numbers starting from 0, 0, 1, 2, 3, and that continues to infinity. The integers, which we use Z for that, have all the natural numbers, 0, 1, 2, 3, and also has all the negative numbers, -1, -2, -3, and that continues to negative infinity. The set Z plus is the set of positive integers, so the 0 is not included. Just start with 1, 2, 3, and that continues. And then R is the set of real numbers, which all of the above sets are subsets of the real numbers. We use bold R for the set of real numbers. R plus is a set of positive real numbers, so these are all the real numbers larger than 0. C is the set of complex numbers. We will not be working with complex numbers, but this is a set larger than R, but this is not the subject that we will study. Finally, Q is the set of rational numbers, any number that can be written as a fraction. A over B with B doesn't equal 0. Is the set of rational numbers, or the set of fractions. We already have seen several examples of sets. There's different ways to describe a set. One way to describe a set is using set builder notation. Specify the property or properties that all members of the set must satisfy. We have already seen several examples. For example, the set S is the set of all x such that x is a positive integer less than 100. T is the set x such that x is an odd positive integer less than 10. The set O is x in Z plus such that x is an odd integer, x is odd and x is less than 10. Also, a predicate can be used to describe the elements of the set. For example, some predicate P of x. S contains the set x such that satisfy the predicate P of x. Here is an example. S is the set x such that prime, the set of all prime numbers. Positive rational numbers can be described this way. Q plus, which is a set of positive rational numbers, is x in R such that x equals p over q for some positive integers p and q. Also, intervals are sets of real numbers. We have a notation that we use to describe intervals. If you use square brackets, start with a square bracket, a comma b, and then close with a closed bracket. This is a closed interval. This is a set of all x, all real numbers, x, such that x is greater than or equal to a and less than or equal to b. But this is a closed interval because it contains its endpoints, but that's an example of a set. The next one is a half-open interval. Starts with a and includes a and ends at b, and b here is not included. But this is the set of all x. X is greater than or equal to a and less than b. This one is half-open. It only contains the left endpoint, but it does not contain the right endpoint. Here is another half-open interval. This time this is the same interval. This is a set of all numbers greater than or equal to. This is that does not include a, but this is a set of all x larger than a and less than or equal to b. The final example, the 4-line, is an open interval because it does not contain either of the endpoints. This is a set of all points greater than a and less than b. All of these are examples of intervals. And intervals are just subsets, and that's normally the standard way to describe an interval. The other set builder notation can be used to describe sets. There may be more than one way to describe the same sets. Here are two examples of describing a set. If we take the set A that has numbers 1, 4, 9, 16, 25, and that continues, this looks like the square of the positive integers. So you can write a as x, such that x is equal to n squared. N is a positive integer. That gives you the same set. For the second set, this consists of letters A, D, E, H, M, O. You can make up a word out of the letters, such as Muhammad. B is the set x, such that x is a letter of the word Muhammad. This is one way to describe the set. Or just, since there is a limited number of letters, you can just list them. Describing a set, we use what's called Venn diagrams to describe a set. Actually, Venn diagrams are very useful when you work with sets. You can use them to describe sets, and also some set identities can be at least you can display or exhibit the identity using Venn diagrams. What is a Venn diagram? There's one in the slide. The rectangle here represents the universal set. This is the underlying set we're working with. The set itself can be represented by a circle or something close to a circle. Here, for example, you can think of the universal set as the set of integers or positive integers. S is the set of the primes 2, 3, 5, and 7. This is the same set as prime numbers less than 10. If the universal set is known, you don't even need the rectangle. You can just use the circle and just place or list the elements inside the circle. We already saw this notation. X belong to S. This is how we write it. X is an element or a member of the set S. For example, 3 is an element of the set of natural numbers. The letter A is a member of the set or belongs to the set X, such that X is a letter of the alphabet. to say that an element does not belong to a set, we use the same notation, but we cross it. For here, this statement here says that X is not an element of S. Of course, we like to use logical statements to describe some of the notation. But X is not an element of S can be described as the negation of the statement X belongs to S. X is not an S. There are some special sets that we will work with, or we will see, and sometimes we end up with some special sets. The first one is the empty set. We use the Greek letter phi. This is the null set or the empty set. This is just the set containing no elements. Of course, it is unique. You can either use phi to refer to the null set, or you can just use the brackets with nothing inside them. That will give you the same thing. This is the empty set, which means the set that has no element. Here is a note that you should understand. The empty set does not equal the singleton set. This set here, use bracket and then place the empty set. This is not an empty set. It contains one element. The element happens to be a set. This is not the same as the empty set. It's a good idea not to use both notation. Either use phi for the empty set or use empty brackets. And I prefer the phi. This is the symbol used to represent the empty set to avoid any conclusion. Again here, phi is the empty set, but the set that contains the empty set is not an empty set. These are not the same things. Two sets are declared to be equal if and only if they contain exactly the same element. A and B are equal. You can use now a logical statement to describe equality of sets. For all X, X is in A if and only if X is in B. That means every element of A is in B and every element of B is in A. That's what equality is. We've already stated the fact in an order and repetition do not matter, and they don't change the set. The set that has the numbers 1, 3, 5 is the same as the set that has 3, 5, 1 is the same set as that contains 1, 3, 3, 3, 5, 5, 5. Each one of these sets contains three numbers, 1, 3, and 5. Go back to the slide. The subset notation, here you see a line, short line, which means in the subset notation that you allow for the two sets to be equal. And a set can be, and here when you use this notation, S can be equal to T, but of course T can be larger. If you write the same notation without this short line, then what we have here, this is the same notation without the line, without the equal sign, but this is read that S is a proper subset of T. That means S is a subset of T, but T is larger. That means there's an element in T that is not contained in S. Using Venn diagrams to describe the proper subset, here is two circular shapes, or oval shapes. The smaller set is S, the larger set is T. You can see in S is a subset of T, but T is larger. In other words, S is a proper subset of T. Here is another example. The set that has the numbers 1 and 2 is a proper subset of the set that has the numbers 1, 2, and 3. Objects that are elements of a set may themselves be sets. And we started by defining a set to be a collection of objects. But these objects can be anything. They can be numbers, letters, chairs, and they can be sets. A set then can be a collection of sets. And here is an example that describes this. Suppose you start with a set. You have a set that contains maybe the numbers 1, 2, 3. Now if you take the collection of all subsets of that set, the result will be a set, and the members of that set will be subsets. Basically they're subsets of the set that has 1, 2, 3. Now it's easy to list all the members of S. These are all subsets of the set 1, 2, 3. The empty set will be 1, but then you can list the singletons, the subset that have one number. So this is a set that contains 1, the set contains 2, the set that contains 3. Then list the subset that has 2 elements, 1, 2, 1, 3, and 2, 3. And then list the element, the set or the subset that has all the numbers, 1, 2, 3. Notice that phi and the set itself are subsets of the set, so they're included in S. There is 8 elements in S, and S is just a collection of sets. These are the subsets of the set that has 1, 2, 3. Later on we'll call this the power set, starting with the set 1, 2, 3. The power set is a collection of all subsets of the set you started with. Here is an example of where you have a set, and the elements of that set are just subsets of something or of another set. Here is another thing to keep in mind. 1 does not equal the set that has 1. This should be clear. 1 is a number, while this is a set. The set that contains 1 is a set, but these are not the same. Also, the number, the one in the middle, is a set that contains 1, while the set to the right is a set that contains 1 element, but it is a set. The members of the set in the middle are numbers. The members of the set to the right are sets. So these are not the same things. Another thing we need to consider about sets is the cardinality and finiteness. Finiteness, a set can be finite, as we have seen, and it can be infinite. If the set is finite, we can talk about the cardinality, which means how many different elements of S. If the elements is repeated more than once, we only count it 1. For the symbol that we use what looks like the absolute value, but it's not. This is the cardinality of S. Use bars, enclose the set in 2 bars. That is read the cardinality of S, which basically means that how many different elements of S. This is the number of elements, the number of distinct elements in the set S. Here are some examples. The cardinality of the empty set is 0 because it has no elements. The cardinality of the set that has the numbers 1, 2, 3, 5 is equal to 4. This set has 4 elements. The cardinality of the set that has the letters A, B, C is 3 because it has 3 elements, 3 objects. But be careful now with this last example. We are taking the cardinality of a set. The members of this set are the sets themselves. There's actually 2 sets in that set. For the cardinality of this set is equal to 2. This happens to be a set such that the members themselves are sets. There is 2 sets, but then there is 2 objects, for the cardinality is equal to 2. The power set, we started actually by giving an example of a power set. The power set P of S of any set S is the set of all subsets of S. For example, the one we did a while ago. So S, you start with a set. You can form now the power set by taking all possible subsets of S. Here are examples. مثلا the set you start with is a set that contains the letter A. There is actually two subsets, the empty set and the set itself. The power set of the set that has the two letters A, B. Of course, you always include the empty set and the set itself, but there are two more subsets, the set that contains A and the set that contains B. These are all the subsets of the set that has A, B. This is the one we already did. The power set of the set that has 1, 2, 3 are the subsets that we listed in the previous example. There should be 8 subsets. And again, you always include the empty set and the set itself. So in this case, there are other subsets. This is a listing of all the subsets. All the subsets of the set 1, 2, 3 are the element of the power set of that set. Here are some tricky ones. The power set of the set whose only element is phi, there is two subsets, phi, the empty set, and the set itself. The set that we started with is the set with one element, which is phi. For the power set has two subsets, phi and the set itself. Now the power set of phi, there's only one subset of the empty set, which is the set itself. The power set can be formed. You can count the elements or the cardinality of the power set if you know the cardinality of S that you started with. If you start with a set that has n elements and S has n elements, then the power set of S should have 2 to the n elements. And this formula works. Our first example, A has 1 element, but the power set has 2 to the 1 or 2 elements. The second example, we started with a set that has 2 elements. The power set has 2 to the 2, which is 4. The third set has 3 elements. The power set has how many? 8 elements, which is just 2 to the 3. It works also for this set, and even the empty set. The cardinality of the empty set is 0, so the cardinality of the power set of the empty set, the number of elements is 2 to the 0, which is equal to 1. This formula works for all values of n, including 0. Here is one more time. If you start with a set S that has n elements, then the number of elements in the power set of S is 2 to the n. This formula is useful because sometimes you want to know how many elements are in the power set, but you don't want to list them all. That might be a larger number, but this formula allows you to count how many sets are in the power set of a set. This is in terms of the cardinality of the set you started with, the cardinality of S. Now we started with sets, and we said that the order is not important. Now we have another type of object. These are ordered n tuples, and from the name here it should be clear and the order is important. An n tuple, for the n here is how many elements that you use. So here is the definition: an ordered n tuple. Here you have to use round bracket. These are different than the brackets for the set. So these are ordered set or ordered sequence of numbers, A1, A2, all the way to AN. For this ordered n tuple is the ordered collection, meaning an order that means you have the first element is A1, A2 is the second element, A3 is the third element, until you reach the last element, which is AN. So here order is important, and also repetition is important. This is definitely different than the concept of a set, because order and repetition do count. These are like set, except duplicates matter because it changes the dimension, and also the order makes a difference. An example of an n tuple, if you have, طبعا again use round brackets, 2, 5, 6, 7 is an example of a 4 tuple. طبعا 4 لأن you have 4 numbers. Here in this 4 tuple, the first element is 2, the second element is 5, the third element is 6, and the fourth element is 7. طبعا because order is important, then here طبعا we call this an ordered pair. If n is 2, we call it an ordered pair. The ordered pair 1, 2 does not equal or is different than the ordered pair 2, 1. If you compare the first and first element, they will be different. So these are two different ordered pairs. The next one, the one to the far right, is not even an ordered pair. Here, this is a 3 tuple. So it's definitely not the same. As we stated, the 2 tuple, and when n is equal to 2, we call them ordered pairs. Next, we would like to define Cartesian products. This is an operation on sets. The Cartesian product of any two sets, A and B, is defined to be the set of all ordered pairs AB, such that A comes from the set A and B comes from the set B. We use the same, we use a cross or a product to indicate the Cartesian product. This is an operation between sets. In fact, it is a binary operation. But let's repeat the definition. The Cartesian product of A and B is the set of all ordered pairs AB, such that A comes from the set A and B comes from the set B. Here is a simple example. If you take the Cartesian product of the set that has the two letters A and B times the set that has the numbers 1 and 2, the set of all ordered pairs can be listed. Take A with 1, A with 2, B with 1, and B with 2. These are all the ordered pairs that satisfy the condition for the Cartesian product. As far as the number of elements you will get in the Cartesian product, the cardinality of A times B is equal to the cardinality of A times the cardinality of B. And the number of elements in A cross B is equal to the number of elements of A times the number of elements of B. In our case, it is 2 times 2, which is equal to 4. Since the Cartesian product consists of ordered pairs, the Cartesian product is not commutative, which means A cross B or A times B is not the same as B times A. That should be clear because A times B, A cross B, and B cross A has different elements. Here is performing the product in the other order. If you multiply now the set 1, 2 times the set AB, you still get 4 ordered pairs, but they are different looking pairs. They start with a number, and the second element is a letter. But certainly the Cartesian product is not commutative. A cross B does not equal B cross A. You can extend the idea of Cartesian product to n or finite number of products. You can multiply, if you have sets A1, A2 up to AN, you can define the Cartesian products of these sets to be the set of all ordered n tuples where the ith element comes from the ith set. Here AI belongs to the set AI for all of the values from 1 to n. We will look at an example of multiplying 3 sets, but the idea can be extended to more than 3 sets. Here are we will look at the products of 3 sets, A times B times C, where A is the set 0, 1, B is the set 1, 2, C is the set 0, 1, 2. The product of these 3 sets is the collection of all 3 tuples where the first elements come from A, the second elements come from B, and the third element comes from C. Here is a listing of all such elements. طبعا if you want to count how many 3 tuples, you multiply 2 times 2 times 3. That should give you 12 elements in the Cartesian product, A times B times C. Next, we will do more operations on sets. So we will do the union and the intersection. Starting with the union, the symbol we use for that looks like a letter U. This is a union operator. Yani you apply the union to two sets. You write A union B. The definition here of the union, for any two sets A and B, A union B, and this is the symbol we use, is the set of elements that are either in A or in B or both. The way to define it using logical statements, A union B is X such that X is in A or X is in B. طبعا this is inclusive OR, it will include X that is in both sets. Here is a numerical example, and also using Venn diagrams to show the union. The first set has the numbers 2, 3, 5. That's A. The second set has the numbers 3, 5, 7. The union contains all the elements of A plus all the elements of B. طبعا some of them are repeated. You can still, 2, 3, 5, 3, 5, 7. This is just taking all the elements of A plus all the elements of B. You can write it without the repetition. This is the set 2, 3, 5, 7. طبعا in the union, each of these elements is either in A, or it is in B, or it is in both. Here is Venn diagrams that describe the union. Notice we didn't use a universal set. It is clear we're talking about positive integers or integers. طبعا you can either set, but it's very clear what the universal set is. The first set is represented by the first circle. It has 2, 3, 5. The second set has is the second circle, 3, 5, 7. The union, of course, is represented by the shaded area. Take all the elements 2, 3, 5, 7 that represent the union. The next operation is the intersection. We use the symbol for that. Looks like a U that's upside down, the opposite of the union. But this is again is a set operation. If you have A and B, the intersection, which is written this way, A intersected with B, is the set containing all the elements that are both in A and B. With the union, it is OR, A or B. With the intersection, it is A and B. You take the elements that are common to both sets, the elements that are in the first set, and also at the same time they have to be in the second set. The logical statement that describes the intersection, A intersected with B is X, such that X is in A, and this time use and, X is in B. Here is an example. If you intersect the set A, B, C with the set 2, 3, the intersection is empty. They have nothing in common. The first set contains letters, the second contains numbers, but they have nothing in common. Their intersection is empty. In this case, when the intersection of two sets is empty, we say that they are disjoint. They have nothing in common. The second example, if you take the set 2, 4, 6, intersect it with the set 3, 4, 5, the only element in common to both sets is the number 4. So the intersection is the set containing the number 4. Venn diagrams describe the intersection. The set, you have your two sets. The first circle is 2, 4, 6. The second is 3, 4, 5. The only common element is 4. This is shaded. The intersection is shaded in Venn diagrams. How do you count the number of elements of A union B? Here is the formula. The number of elements in A union B is the number of elements in A plus the number of elements in B minus the number of elements in the intersection of A and B. The reason for that is that if the two sets are not disjoint, there are elements that are counted twice. And if you add the number of elements of A plus the number of elements of B, there are some elements which were counted twice. These are the elements in the intersection. So you have to subtract the number of elements in the intersection. And here is an example that demonstrates the formula. If you take the union of the sets 1, 2, 3 with the set 2, 3, 4, 5, you can take the union to be, you can list it without repetition. Here clearly you have some elements in common, such as the 2 and 3 are common to both sets. The union here is the elements 1, 2, 3, 4, 5. The intersection has the two elements 2 and 3. If you add the number of elements of the first set, which is 3, plus the number of elements in the second set, which is equal to 4, subtract the number of elements that is in the intersection, which is 2, the result should be 5. And it's clear that the union of the two sets has 5 elements. Now, before we continue, if the two sets happen to be disjoint, the intersection would be empty. The number of elements in the intersection is 0. In this case, the number of elements of A union B is equal to the sum of the number of elements of A plus the number of elements of B. This would be the special case. The next operation is set difference. If you have two sets A and B, the difference of A and B, which we write as A minus B, is the set of all elements that are in A but not in B. Using logical statements, A minus B is defined to be X, such that X is in A and X is not in B. Equivalently, you can write it as X, such that not X is in A implies X is in B. The other thing, the difference A minus B can also be written as A intersected with B complement. We haven't defined the complement, but we are taking everything in A that is outside B, not in A. You are excluding the elements of B. A minus B can be written as A intersected with B complement. You can think of A minus B as the complement of B with respect to A. Here is an example, numerical example, and also a Venn diagram describing the difference. We take the set that has the numbers 1, 2, 3, 4, 5, 6 minus the set 2, 3, 5, 7, 9, 11. You want to start with A. Take every element of A provided that it's not in B. You can certainly take 1 because it's in A but not in B. You cannot take 2 or 3 because they are in B. You can take 2 and 3 are excluded. You can take the 4 because it's in A but not in B. You can also take the 6. The 5 cannot be taken because it is in B. And then you can also take 6 because it's in A but not in B. In Venn diagrams, you have the set to the left is A, the set to the right is B. The set difference is this highlighted area. This represents every element that is in A but not in B, everything in A that is not in B. This is called the set difference. It should be clear, of course, that A minus B is different than B minus A. Using the set difference, you can define another operation called the symmetric difference. The symmetric difference, we use the symbol for XOR. We use it in this case for sets. It's called the symmetric difference. the set of all elements that are in A but not in B, or in B but not in A. And basically you take A minus B union B minus A. For the symmetric difference, A with B, and again we use the symbol for XOR, but this is actually read the symmetric difference of A and B is X such that X is in A and X is not in B. This is just A minus B. Or X is in B and X is not in A, and that is B minus A. Another way to look at the symmetric difference, this is actually if you take everything, if you take A union B and remove the intersection, you are left with A minus B union B minus A. So that gives you the symmetric difference. This identity is one way to form the symmetric difference is just take the union and remove the intersection. One more time, the symmetric difference of A with B can be written as A minus B union B minus A, or you can write it as A union B minus the intersection of A and B. Here is an example where you can apply the symmetric difference to two sets. The first set is 1, 2, 3, 4, 5, 6. The second set is 2, 3, 5, 7, 9, 11. The first part, you start with A, select the elements of A that are not in B, and then go to the second set and select the elements that are in B but not in A. But the result should be 1, 4, 6, 7, 9, 11. If you look at an easier way to form the symmetric difference is take the union, take everything, and remove the common things. Remove the elements that are in the intersection. Take everything and remove, in this case, you could remove the 2, the 3, and the 5. So you're left with 1, 4, 6, 7, 9, and 11. The next concept that we use for sets is the set complements. If you have a set A, then the complement, you write A with a bar above it. This is called the complement. If A طبعا is a subset of the universal set, the complement of A is just U minus A. But this is the set of all elements that are in U but not in A. You can think of it as all the elements that are outside A. طبعا outside A but in the universal set. The easiest way to write the complement, A complement is X such that X is not in A. But طبعا it's understood that X will be in the universal set. The Venn diagrams showing the complement, the rectangle here is the universal set. The set A is shaded in yellow. Everything outside A but in the universal set is the complement of A. Two things that should be very clear, that A and A complement are disjoint. They have nothing in common. And their union will give you the universal set. Every element in the universal set is either in A or it is in its complement. Here is an example. If the universal set is N, the set of natural numbers, what is the complement of the set that has 3 and 5? Well, it's every natural numbers except 3 and 5. So you can take 0, 1, 2, skip the 3, take 4, skip 5, then take 6, 7, and the remaining natural numbers. The complement of the set that has 3 and 5 is every natural number that is different than 3 and different than 5. Here is a problem that, or an example that kind of reviews some of the operations we looked at. طبعا if you see the graph here, or the picture gives you the solution. but yeah, to read this, you will see that you will be looking at the several operations that we looked at. So here the problem is we want to find A and B. These are two subsets of E. E is your universal set. A and B are subsets of E, such that the intersection of A and B has the elements 1 and 2. The A has 3 elements, B has 4 elements. The complement of A has the numbers 3, 4, 5, and 9. The complement of B has the numbers 5, 7, and 9. We want to find the sets A, B, and the universal set. Well, every element was mentioned, every number that's in any of these sets will include, the universal set will include all the numbers that are listed here. So the universal set will have the numbers 1, 2, 3, 4, 5, 9. All of these are in the universal set. The way to solve this is you need to draw a rectangle that represents E, draw 2 circles, one for each set, and you have an intersection between them. You can go ahead and fill the intersection because we know that the intersection of A and B has the numbers 1 and 2. And now go through the numbers and see if they are in A or outside A, if they are in B. You already have listed the intersection. All the elements will be either in A but not in B, or in B but not in A, or they are outside both A and B. Starting with the number 3, 3 is in the complement of A, so it's outside A, but it is not in the complement of B, so it must be in B. You can go ahead and list or write 3 in the set B. What about 4? 4 is in the complement of A, so it's outside A, but it is not in the complement of B, so it must be in B. So the number 4 is in B. Then 5. 5 happens to be in the complement of A, so it's outside A, and also it is in the complement of B, so it's outside B. So 5 is outside both A and B. So you just write it outside A and B. What's the next number that you see here? The number 7. 7 is not, well, it is in the complement of B. So it is outside B. It is not in the complement of A, so it must be in A. Now you have accounted for all the numbers. For the set A has the numbers 1, 2, and 7. The set B has the numbers 1, 2, 3, and 4. And the outside both sets is the numbers 5 and 9. The universal set has all these numbers 1, 2, 3, 4, 5, 7, and 9. This is an example. If you can solve it, this would be a good review for many of the concepts that we covered that deal with sets and set operations. Here's another example, which is basically a review of the different operations. The universal set here has the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It has all the digits from 0 to 10. A has the numbers 1, 2, 3, 4, 5. B has the numbers 4, 5, 6, 7, and 8. The union has all the elements from A or from B or both. It should have 1, 2, 3, 4, 5, 6, 7, and 8. That's the union. The intersection are the elements that belong to both A and B, and these are just 4 and 5. The complement of A, remember the universal set is from 0 to 10, but the complement of A are those elements in the universal set that are not in A. So you can take 0, you cannot take 1 through 5, take 6, 7, 8, 9, and 10. These are all the elements that are in the universal set, but not in A. The complement of B is everything in the universal set, but not in B. So you can take 0, 1, 2, 3. You cannot take 4, 5, 6, 7, and 8. You can take 9 and 10. That's the complement of B. A minus B is everything in A that is not in B. So you can take 1, 2, 3. These are all the elements that are in A but not in B. B minus A, you want all the elements that are in B but not in A. طبعا you can exclude the 4 and the 5 and take 6, 7, and 8. The symmetric difference between A and B is just the union of A minus B with B minus A. So you can take 1, 2, 3, 6, 7, and 8. These are the elements of the symmetric difference of A and B. Here are some set identities or rules that we can use with sets. The identity rule says A union the empty set is equal to A, and A intersected with the universal set is also A. Domination, A union the universal set equals the universal set. A intersected with the empty set is the empty set. Idempotent, A union A is equal to A. A intersected with A is also equal to A. The double complement, the complement of the set is equivalent to the set or equal to the set. The commutative, A union B equals B union A. A intersected with B is the same set as B intersected with A. The associative, A union, the union of B and C is equal to A union B union C. Yani you can take any two sets and form the union, and then take the union of the third set. In this example, in this case, you don't even need to use parentheses, just write A union B union C. Same thing for intersection. A intersected with the intersection of B and C is equal to the intersection of A and B intersected with C. And here also you don't need to write parentheses, just write A intersected with B intersected with C. A distributive law says A union the intersection of B and C is A union B intersected with A union C. Next distributive law, A intersected with B union C is equal to A intersected with B union A intersected with C. De Morgan law for sets, the complement of A union B is equal to A complement intersected with B complement. Here, as you can see, to complement the union, apply the complement to each set, and the union becomes the intersection. The complement of the union is the intersection of the complements. The second De Morgan law, the complement of the intersection is equal to the union of the complements. Yani the complement of A intersected with B is A complement union B complement. To prove set identities, think of an identity as an equation where the left-hand side is a set E1 and the right-hand side is also a set E2. So to prove the identity, you are proving E1 equals E2. But you can do that, one way to do this is proving that E1 is a subset of E2 and E2 is a subset of E1 separately. Second method is using set builder notation and logical equivalence. In this case, you start with one side or one set, use set builder notation. In each step you replace the set by an equivalent set, and in the last step you should get the second set. Third method is using set identities. Here's an example of proving identities. We want to show that the complement of A intersected with B is A complement union B complement. By proving the left-hand side is a subset of the right-hand side and the right-hand side is a subset of the left-hand side. To show that the left-hand side is a subset of the right-hand side, just pick an arbitrary element in the left-hand side, the complement of A intersected with B, and show that it belongs to the right-hand side. which is A complement union B complement. Here you use the definitions of the different operations. For X in the complement of A intersected with B means X is not an A intersected with B. That means, what does it mean for an element to be not to be in the intersection? That means it is not in one of them. It's not either it's not in A or it's not in B. This can be written that X is not in A or X is not in B. If X is not in A, then X is in the complement of A. If X is not in B, then X is not. If X is not in B, then it is in the complement. But either X is in A complement or X is in B complement, which means X is in A complement union B complement. The other way to show the right-hand side is a subset of the left-hand side, you just reverse the steps. Start with X belongs to A complement union B complement. That means X is in A complement or X is in B complement. That means either X is not in A or X is not in B. That means X cannot be in the intersection of A and B, and therefore it has to be in the complement of A intersected with B. This is the same formula. We want to show that the complement of the intersection is equal to the union of the complements. This time we want to use set builder notation. And what that involves is use the definitions and each step write an equivalent set until you reach the second side. And you start in the left hand side, each step replace the set by an equivalent set until you reach the right hand side. For the first step, the complement of A intersected with B by definition is X, such that X is not not in A intersected with B. X, you don't need all these steps. X not in the intersection of A intersected with B means either X is not in A or X is not in B. That means X is in A complement or X is in B complement. In this case, of course, then X must be in the union, A complement union B complement, and that's the right hand side. So we started with the left hand side, use the definitions of complement of the intersection until we reach the right hand side. There is nothing else to do, and you have already proved that the left hand side is equal to the right hand side. Here is the third method, is using set identities. We want to show that the complement of A union B intersected with C is equal to C complement union B complement intersected with A complement. Start with the left hand side. First apply the complement to the union using De Morgan law. You should get A complement intersected with B intersected with C. Here we are applying it to the union, so it's the complement of the first set. It is A complement intersected with, union becomes intersection, the complement of the second part, which is B intersected with C. This is applying De Morgan law to the union. Next, apply De Morgan law to the intersection, which is in the bracket. You get A complement intersected with B complement union C complement, and intersection becomes union. Now all what you have to do to get the right hand side is change the orders. So write B complement union C complement first, write B complement union C complement intersected with A complement. This is just using the commutative law for the intersection. You're just changing the order of the two sets. The last thing you need to do is change the order inside the bracket. Write it as C complement union B complement, and you get exactly the right hand side. Using set identities, you can prove some identities like the one we just did. Okay, here is another one. We want to show that B union C minus A is equal to B minus A union C minus A. The first step is we can write, we already know the formula that we will apply, B union C minus A is the same as B union C intersected with A complement. We have already covered that for that law or that formula. Now use the distributive law. طبعا here the intersection with A complement, you can apply the distributive law to the bracket. But this can be written as B intersected with A complement union C intersected with A complement. And now write this back as a set difference. B intersected with A complement is just B minus A. C minus A complement is just equal to C minus A. And that gives you the right hand side. The third method or fourth method to prove set identities is using membership table. I will not do any details. We usually don't cover this method, but you can read about it. But basically the idea that you can have, if you have an identity, you can have a column for each set, and you may have to take مثلا B intersected with C. Yani take the sub expressions, have a column for them, and those zeros and ones actually refer to membership. Yani you can take X, for example, in elements of the universal set. If it doesn't belong to A, use 0. Doesn't belong to B, use 0. Does not belong to C, so use 0. In any case, for any set, if the element belongs to the set, use 1, because that's true. If the element does not belong to the set, then use false. Doing that for each part and comparing, you can think of these as truth values, then the membership list is the same. Any element that belongs to the left-hand side belongs to the right-hand side, and any element that belongs to the right-hand side will also belong to the left-hand side. This is not a bad way to prove identities, but I cannot take any more time. You can read about it in the book. There is more details. Probably it's a good idea to start with a smaller example. This is a rather large table, but start with the simpler identities. This is not a bad way to prove set identities. Here is an example of an application that relates to sets, which is computer representation of sets. طبعا, as you would suspect, a computer will represent a set using zeros and ones. So here is how we do it. Let the universal set be the numbers 1 through 10. We will, طبعا, since the universal set has 10 elements, then we need bit strings of length 10. طبعا, just to remind you, a bit string is a sequence of numbers that uses only zeros or ones. So you need a bit string of length 10 to represent any subset of U. So the way to do this, if you take any subset of U, go through every element of U. If the element belongs to the set, then use 1, and if it does not belong to the set, use 0. So here is my universal set, 1 through 10. Let's take A to be the set that has the numbers 1, 3, 5, 6, and 9. Now to represent A, this is how we'll do it. We'll go through every number in the universal set and see if it belongs to A or not. If it does, write 1. If it doesn't, write 0. طبعا for 1 belongs to the set, so you use 1. 2 does not, so use 0. 3 belongs, so use 1. You continue. You'll end up with a bit strings of length 10. This represents طبعا for each elements of U. If it belongs to A, then 1 is used, and if it does not belong to A, 0 is used. But here is the string we end up with. It has 10 digits, and that is the representation of the set A.
In this tutorial, we will continue topics from Chapter 2, we will cover functions, and also we will cover matrices. The definition of a function that we are used to, we start with two sets, A and B. A function from A to B is an assignment of each element of A exactly one element of B. And we write it as f of A equal B. If B is a unique element of B assigned by the function for the element A. So there's actually two conditions here, that each element in A must have an image in B, and it has to be a unique image, meaning every element is assigned only one value in B. Functions are called sometimes mapping. We say that f is a map from A to B, or a transformation. Here is a quick example of a function. The first set is a set of students. The second set is a set of grades, letter grades, A, B, C, D, E, F. Here the function assigns where each student assigns a grade. Of course, each student is assigned a grade, only one grade. But that fulfills the conditions for a function. We will look at other examples and other ways to represent functions. The definition that we will use now for a function is different in the sense that it uses sets. Of course, we already covered ideas about sets and how to form the Cartesian product, so we can use that to define a function. A function, again, from A to B can be defined as a subset of A times B, A cross B. And in this sense, you can think of it as a relationship. Just to remind you, A cross B means the set of all ordered pairs such that the first element comes from A and the second element comes from B. Now, for this to be a function, there is two conditions, exactly like the other definition. A function from A to B must contain one and only one ordered pairs, A, B, for every element in the first set A. To use logical statement to describe a function, for all x is in A implies that there exists a y such that y is in B and the ordered pair x, y is in the function. That means every element is assigned a value. Every element in A must be assigned a value in B. Now, the uniqueness condition that every element in A is assigned a unique value in B can be written using a logical statement. For all x, y1, y2, if x, y1 is an ordered pair in the function, and if x, y2 is also another pair in the function, here y1 must equal y2. In other words, if y1 is the image of x under the function, and if y2 is also the image of x, the same x, then y1 and y2 must be the same. You can only assign one value in the second set for each value x in the first set. There are some definitions that we use when we work with functions. We say that f, if you have a function from A to B, we say f maps A to B, or f is a mapping from A to B. Now, the first set is called the domain of the function f. B is called the codomain of f. If f of A equal B, meaning here A is an element of capital A, the first set, B is an element of the second set. F of A equal B, that means B is the element that is assigned by the function to the element A. B is called the image of A under F. A is called the pre-image of B. The range is a set of all images of points in A. So the range is a subset of the codomain. It does not have to be, there could be, the codomain could be larger. Of course, if they're equal, we give the function a special name, we call it onto. every element in the codomain gets hit. Two functions are equal if they have the same domain, same codomain, and they do exactly the same thing to each element. But they map each elements of the domain to the same elements of the codomain. How to represent functions, we saw an example already, an explicit assignment. You can do this if you have a finite domain and codomain. Each student is assigned a grade. The way that we represent functions that we are more familiar with is using a formula. A formula something like f of x equal x plus 1. So here f is the name of the function. It could be anything. It could be g of x, it could be h of x. We write it this way to emphasize or to show that the function depends on the variable x. F of x equal x plus 1 is an example of a function. There is a third method that we will not use, is using a computer program. You can actually use Java code. You write a Java program that you can this Fibonacci number, there are, but we will not be looking at this. There's also special properties for functions that we'll look at. A function is set to be one-to-one if it maps different elements from the domain to different elements of the codomain. And you cannot have two different elements of A mapped to the same image. You cannot have two different elements in the domain sharing the same image. There are many examples you can check out for yourself. Here is an example of a function that's one-to-one. The first thing is to convince yourself that this is a function. Second thing, you take any two different elements of the domain, you will see that they are mapped to different images of the codomain. But that makes it a one-to-one function. Okay, here is examples. This is one example of a one-to-one function. Here's another one. F of x equal x minus 1. This is considered to be a function from z, the set of integers, to z, the set of integers. This is to one-to-one. How do you show that? Using logical statements. What you want to do is assume that the images are the same. Assume in the f of a equal f of b, you want to show that a equals to b. F of a is just a minus 1, f of b is b minus 1. If you add 1 to both sides, you get a equal b. And that's how you show a function is one-to-one. The other property for functions we will consider is called surjections. Function from a to b is called onto or surjective if every element in the codomain has a pre-image. Every b in the codomain, there is an element a in the domain such that f of a equals b. In this case, we say that f is a surjection or that the f is onto. Here is an example, the picture. The set A has the letters A, B, C, D. That's the domain. The codomain has the letters X, Y, and Z. We can see that every element in the codomain has a pre-image. There's something from the domain that's mapped to it. The other example we looked at, the function f of x equal x minus 1, we showed that this function is one-to-one. It also happens to be onto. So how do we show a function is onto? You need to take an arbitrary element from the codomain and show that it has a pre-image. Of course, this function is considered to be a function from the set of integers to the set of integers. Now, the way to do this, take any element in the codomain. If b is in z, the codomain, we want to find something that's mapped to b. So what we want to do is take a to be b plus 1. So now f of a is take b plus 1, subtract 1, and you get b. So we have found a pre-image for B. We found an element in the domain that is mapped to it. One more definitions. A function is said to be a bijection or one-to-one correspondence if it is both one-to-one and onto. For example, for this example, it's clearly a one-to-one function because you take different elements from A, they are mapped to two different elements, so it's one-to-one, and also it's clearly onto. There's an example of a function that is considered to be a bijection or a one-to-one correspondence. The other example that we covered, f of x equal x minus 1, we showed that it is one-to-one and onto, so that's a second example of a one-to-one correspondence or a bijection. So to summarize the two properties, to show a function is one-to-one or onto, first for an injective mapping, what you want to show, if the images are the same, then the pre-images are equal. If f of x equal f of y for arbitrary x and y, then x is equal to y. Now to show that the function is not an injection, you want to show or give a counterexample. That means find two elements in the domain, x and y in the domain, such that f of x is equal to f of y. That would be a counterexample that would show the function is not one-to-one. For surjections or onto, to show a function is onto, pick an arbitrary element from the codomain and show that it has a pre-image. Show that there is an x in the domain such that f of x equal y. To show a function is not onto, find a particular y in B, and find an element in the codomain that does not have a pre-image, such that f of x does not equal y for all x in A. That would show it is not onto. Here, let's look at some examples. Example 1, this is a function from a finite set to a finite set. The domain is A, B, C, and D. The codomain is 1, 2, and 3. F maps A to 3, B to 2, and C to 1, and D to 3. F is onto because every element in the codomain has a pre-image. For example, the pre-image of 1 is C, the pre-image of 2 is B, the pre-image of 3 is A. That makes it an onto. But in this example, of course, the function is onto, but it's not one-to-one because both A and D are mapped to the same element, 3. So the function is not one-to-one. Another example of a function that's not onto is the function f of x equal x squared. We are taking this as a function from the set of integers into the set of integers. This function, of course, is not onto because if you consider the negative numbers, for example, take the number negative 1, this does not have a pre-image. There is no integer that you can square to get a negative number. For the function, in this case, it's not onto. We found an element in the codomain that does not have a pre-image. The function also is not one-to-one because you can take, for example, minus 1 and 1 in the domain. The image would still be the same. The image is 1. For the function is not one-to-one. The next idea that we will consider is the idea of an inverse function. Of course, an inverse function, what it does, it reverses the action of the function. You have a function f from A to B. The inverse function, if it exists, would be a function from B to A. So the domain becomes the codomain, and the codomain becomes domain. Of course, you can only define the inverse of a function if it happens to be a bijection. not every function has an inverse. If the function is one-to-one and onto, then you can define the inverse. The inverse is written, this is we write it as f to the power minus 1. Of course, this is not a power. This denotes the inverse function. The way we define the inverse function, using this condition, f inverse of y is equal to x, if and only if f of x equal y. What that means, if f maps x to y, then the inverse function maps y into x. The graph here shows the idea of an inverse function. If you start with an element in the domain, the first set, a, f maps it to f of a. F of a. Now what the inverse function does, if you apply the inverse function, it takes you back into the element you started with, a. And that works both ways. If you apply f first and then f inverse, you get a. If you apply f inverse first and then f, you're back to the same element you started with. Here are examples of inverse functions. This is f, a function from a to b. This is clearly one-to-one and onto. It is a bijection. You can define the inverse function, and the inverse function exactly reverses the action of the function. For example, f maps a to y, f inverse maps y back into a. F maps b into w, f inverse maps w back into b. For every element, if you start with the domain, apply f, the image of that element under f is an element in the codomain. If you apply the inverse function, you are back to the same element. Let's look at more examples of inverse functions. This is the one we already looked at. F is a function from the set that has a, b, c. The codomain is 1, 2, 3, and the function is defined to be f of a equal 2, f of b equal 3, f of c equal 1. The function is, you can check, it is one-to-one and onto, so it is invertible, meaning the inverse exists. And of course, to define the inverse, what you want to do is reverse the action of f. For example, f inverse will be a map now from the set 1, 2, 3 to the set a, b, c. F inverse of 1 is equal to c, because f of c equal 1. F inverse of 2 is equal to a, because f of a equal to 2. And f inverse of 3 is equal to b, because f of b is equal to 3. Another example of a function that is invertible is the map f from z to z, defined by f of x equal x plus 1. This function is easily shown to be one-to-one and onto. The way to find the inverse, what f does, it adds 1 to each number. For f inverse, what it does, it will subtract 1 from each number. f of x equal x plus 1. What f does is it adds 1 to each number. F inverse now will do the reverse. It will subtract 1 from each number. And you can easily check that if you apply f first and then f inverse, you get the same number you started with. The third operation that we can use with functions is the composition of functions. Using the composition of functions, you can create new functions. And the idea for this to work, of course, you start with you have 3 sets. You start with a function g from the set A to the set B. You have a second function f from B to C. For this to work, of course, the range of G must be a subset of the domain of F. And the way that you can create the composition is for each element in A, you first apply the first function g, and to whatever result to the image of A under G, you now apply F. You end up with an element in set C. The composition then will end up being a function from the first set A to the third set, which is C. F circle G will be now a function from A to C. And the way, of course, to define it is apply G for each element in the set A, which will be the domain. Apply G first, and then to the image of that element under G, you apply F. Here is an example of forming the composition of two functions. First function G is from the set A, B, C to itself. The way G is defined, G of A is equal to B, G of B is C, G of C is A. The second function F starts from the set A, B, C to the set 1, 2, 3. The way F is defined, F of A equal 3, F of B equal 2, and F of C is equal to 1. Now we want to form both the composition of F and G and also the composition of G and F. Of course, the order is important. First of all, F circle G, which is F of G of X, is defined this way. Of course, if you apply it to A, that's the same thing as F of G of A. G of A is just B, and F of B is equal to 2. So the composition maps A into 2. F circle G applied at B is F of G of B. G of B is just C, and F of C is just equal to 1. The composition maps B into 1. For C, F circle G of C is F of G of C. G of C is just A, and F of A is equal to 3. Now the composition is a map from the first set A, B, C to the third set, which is 1, 2, 3, and that's how the composition is defined. If you try to form G circle F, this is not defined because the range of F is not a subset of the domain of G. A second example of the composition, F of X is equal to X squared, G of X is equal to 2X. If you form F of G of X, that means you start with F and replace X by G of X. So you have then X, which is replaced by 2X plus 1 squared. That's the composition F circle G, or F of G of X. If you form G of F of X, that means start with G and replace X by F of X. Here X is replaced by F of X, which is just X squared. You end up with 2 times X squared plus 1. In this case, you can form both F circle G and G circle F, but as you can see, you end up with two different functions. Here is another example. F of X is equal to 2X plus 3. G of X is equal to 3X plus 2. These are functions from the set of integers to the set of integers. F circle G, or F of G of X, is equal to 6X plus 7. G circle F of X is equal to 6X plus 11. And again, here in this case, the composition, you can form the composition both ways, but you end up with different functions. For here, it should be clear that the order of applying the functions will make a difference. And in some cases, you cannot form both F circle G and G circle F, and sometimes you can form both compositions, but you end up with two different functions. Graphs of functions. If you remember the way we define the function, it is a set of ordered pairs. You can think of it as having two variables. You can graph the points of a function. Of course, if you have a finite function, you can graph all the points of the function. طبعا the function here being represented as ordered pairs A, B, where A comes from the first set, the domain, and f of A, which is B, comes from the second set, which is the codomain. Here is one example of a graph. This is f of n equal 2n plus 1 as a function from n, the natural numbers, to n, which is the set of natural numbers. طبعا here you can only, if you have an infinite function, you can only graph a few points. You cannot graph the entire domain. Here is example. For example, this is 0 and 1. This is 1 and 3. This is 2 and 5. These are just a few of the points where طبعا the horizontal axis represent n, and the vertical axis represent the value of the function, which is f of n. Another function we looked at before is f of x equal x squared from the set of integers to the set of integers. Again, here this function has an infinite domain. You cannot graph all the points, but you can select a few points just to have an idea what the graph looks like. You have 0, 0, 1, 1, 2, 4, 3, 4. All of these are points that are on the graph of the function. Some negative values, negative 1 and 1, negative 2 and 4, negative 3 and 9. These are just few points that are on the graph. طبعا this is discrete points because the domain is the set of integers. And you can also see here why this function is not one-to-one, because you can find two values for x in the domain that share the same image. Here are examples of some important functions. The first one is called the floor function. The second one is called the ceiling function. The floor functions to be the way we write it, f of x equal, you include it in bracket and extend the lower corners. This is called the floor functions, and it's defined to be the largest integer less than or equal to x. The ceiling function, f of x equal, use brackets again, but this time extend the top part. This is called the ceiling function. It is the smallest integer greater than or equal to x. The best way to imagine this function is if you look at all the numbers within an interval, the floor will be the left hand side and the ceiling will be the right hand side. Examples for the floor function: the floor of 3.5 is equal to 3 because this is the largest integer less than 3.5. The floor of minus 1.5 is equal to minus 2 because minus 2 is the largest integer that is less than minus 1.5. The graph in this case will be what we call a step function. If you look at any interval, the floor would be the left hand side of the interval. Example, for all the numbers starting from 0 and less than or equal to 1, the floor will be 0. For the interval 1 to 2, for all the numbers larger than 1 and less than 2, the floor will be 1. So you end up getting a step function. Examples for the ceiling function: the ceiling of 3.5 is equal to 4 because this is the smallest integer greater than 3.5. The ceiling for minus 1.5 is equal to minus 1 because this is the smallest integer larger than or equal to minus 1.5. And again, in this case, you end up with a step function. Look at all the numbers that are larger than or equal to 0 and less than 1. The ceiling for them will be 1. For all numbers that are larger than or equal to 1 and less than 2, the ceiling will be 2. In both cases, you end up with a step function. The next topic that we will cover is zeros and one matrices. The zeros and one matrices are just matrices, regular matrices, except the entries of the matrix are either 0 and or 1. Yani only those two numbers are used. We will see some applications where we end up with a 0 and 1 matrices. As you would expect, the 0 represent false and 1 represent true. Here is an example of a 0 and 1 matrix. The size of the matrix, of course, is in this case 3 by 3. We have 3 rows and 3 columns, and each entry here is either 0 or 1. With 0 and 1 matrices, we have operations that we can apply to matrices. The first operation is the join operation. طبعا you apply to two matrices. To be able to apply the join operation, both matrices must have the same size. Both have to be m by n 0, 1 matrices. The join operation, we use the same symbol we used for OR. So this is read A join B. The operation is conducted according to the position. Take the take the OR of the ij entry from the first matrix with the ij entry from the second matrix. The result, of course, would be a matrix of the same size, and you apply the OR operation for entries that are in the same position. The second operation, which is the meet operation, again you have to have the same size, and both matrices must be of the same size, and they have to be 0, 1 matrices. The meet operation, we use the symbol for AND. This is read A and B, or the meet of A and B. Again, in this case you apply the AND operation for the entries that are in the same positions. Yani the ij entry from A and the ij entry of B, yani the same position. Let's look at an example that will explain both operations. Here is the first matrix A. The first row is 1, 0, 1. The second row is 0, 1, 0. The matrix B, the first row is 0, 1, 0. The second row is 1, 1, 0. Now remember the join operation, you apply the OR to entries that are in the same position. You end up with, of course, start with the first row, first column. 1 or 0 is 1, 0 or 1 is 1, and you apply this, of course, to each entry. Apply the OR operation to the entries that are in the same position. The meet of A and B, in this case, of course, you apply the AND operations for entries that are in the same position. You end up with getting, for example, 1 and 0 is 0, 0 and 1 is 0, and you continue applying the AND operation for entries that are in the same position. There is another operation that we can apply for matrices called the Boolean Product. It is similar to regular matrix product, except Boolean products are applied for 0, 1 matrices. The condition to be able to multiply two matrices, the condition is similar to the condition we have for regular matrix product. If you start with A that has size m times k, meaning m rows and k columns, this is a 0, 1 matrix. You can multiply it by a second matrix. The condition, of course, that the second matrix, the number of rows in the second matrix must equal to the number of columns in the first matrix. If this condition is true, you can apply the Boolean product. The size of the product, the result, would be m by n. The way to apply the Boolean product, it is similar to يعني normal matrix product, but instead you have to use or instead of plus, and you have to use and in place of the product of numbers. يعني you are taking each entry in the product as a result of multiplying a row from A with a column from B, but using or instead of plus, and using and instead of the product. Here is an example of Boolean product. The first matrix A, the size here is 3 times 2. We have 3 rows and 2 columns. The matrix B has the size is 2 times 3, meaning it has 2 rows and 3 columns. Now each entry in the Boolean product, by the way, the Boolean product we use a circle with a dot or with a dash in it that represents the Boolean products of A and B. Each entry in the Boolean product is the result of multiplying a row from A with a column from B. Example, the first entry here, this is the result of multiplying the first row from A with the first column from B. The second entry is a result of multiplying the first row from A with the second column from B. But as you notice, you use and instead of the product, and use or instead of addition. You do have to do this for each entry. In this case we have 9 entries. Each of them is the result of the multiplying, the ij entry in the product is the result of multiplying the ith row from A with the jth column from B. After you form all those entries, you apply those operations. The result would be the size, of course, here is determined by, since A is 3 by 2 and B is 2 by 3, the product will be a 3 by 3 matrix. After applying those operations, the result would be the matrix that has 3 rows and 3 columns. The next thing we can do is Boolean powers. The Boolean powers, you can apply them only to square matrices, square 0 and 1 matrices. The kth Boolean power, you just multiply the matrix by itself kth times. And for example, a to the power 1 is just a squared is a times a to the power k, you multiply the matrix by itself kth number of times. Now, to distinguish the Boolean power from the regular matrix power, you include the power in a square bracket. Again, the kth power, the kth Boolean power is just multiplying the matrix by itself k times. The product, of course, here is Boolean products. Here is an example of Boolean powers. This is A. Of course, it has to be a square matrix, 3 by 3. To find A, the second power of A, A raised to the power 2, you have to multiply A by itself twice. A squared is just A times A. If you apply the matrix product of A with itself, this is the result. So this is now the second power, or A raised to the power 2. Of course, here we are dealing with Boolean products or Boolean powers. Now you can, of course, define if n is a positive integer, you can define the power, the Boolean power, to any positive integer. Here is an example starting with the square matrix A. This is a 3 by 3 matrix. We are asked to find the nth power of A for all positive integers n. Start by taking the second power. A squared is just a times a. This is the result. Now the third power, you can just multiply a squared by a, and you can compute any power by taking the previous power and multiplying it by a. You end up getting the product of a squared with a will give you the third Boolean power. This does not continue forever. By the time you reach the fifth Boolean power, all the entries becomes 1. Now, in this case, any higher power, yani a to the 6th, to the 7th, to the 8th, will give you the same matrix. It will give you a5 for all positive integers larger than or equal to 5.